Welcome back to my YouTube channel all about VLSI. In this particular video, we are going to continue with our Ethernet MAC controller design, where we are going to start with our first module, Verilog Development, that is our CRC generator. Now, before going to discuss about the CRC generator, we need to understand few more things over here. In the CRC process, we have already discussed how to perform serial CRC and how to perform parallel CRC. So basically, Ethernet CRC does not directly transmit the raw CRC register that we have already seen, and IEEE 802.3 defines initialize the CRC register with this particular value. And next step two is we need to feed all the payload bytes. We need to feed, and next we need to invert the final CRC after calculation the CRC. We need to flip all the particular CRC bits and we need to transfer. So this is the steps which we are going to follow when we are going to develop our Verilog code. And when we are going to receive the CRC, there is something known as CRC32 magic residue. So basically, it is an error detection mechanism used in Ethernet frames. That is, CRC is nothing but it's a error detection mechanism that we have already seen. Now, the transmitter computes a frame check sequence, a 4 byte checksum over the frame data, and aperture at the end that we have already discussed it. And the receiver recomputes the CRC and it is going to check for the errors, right? And while we were calculating, we were getting reminder is equal to 0. It is a valid frame, or if it is, we are not going to get 0, it's an invalid frame. Now, there is something known as magic residue concept where normally a receiver could strip off the lost 4 bytes, recompute CRC over the data, compare with the received FCS. But there is more elegant approach that we are going to feed the entire frame, including the FCS, into the same CRC engine. And if no errors occur, the CRC accumulator will always settle to a fixed constant, which is nothing but our magic residue. So this is what particular concept we are going to see about. And what is this magic residue? I will show you when we are going to develop the code. Now, what are the modules which I'm going to have in the CRC engine is I'm going to have a transmit underscore FCS and receiver underscore FCS. So I'm going to have two different modules like this. And this transmit underscore FCS and receiver underscore FCS is going to have one more module which is known as CRC32. The CRC32 is going to calculate the CRC of whatever the data which we are going to send. So this is the modules which we are going to send. Let's see those particular modules and let's try to understand how we are going to build them. Now, as I've said you, so I'm going to have a particular TX underscore FCS. This is my transmitter FCS model, which I'm going to, where it is going to have clock reset, active low reset, and another is init. Basically, this init is a pulse for it, where it is made to one for one cycle to reset the CRC for new frame. And next is data valid. That is whatever the payload data which the user is sending, it's a valid data further. And next is 8-bit data in. So here we are not going to directly perform the CRC. So we are going to perform CRC on a 1 byte data on each and every byte of data. Next is FCS underscore out. Whatever the CRC we have calculated, that is my output FCS underscore out. Next is FCS underscore valid. That is whatever the data which I'm going to or whatever the CRC calculation which I've done is a valid FCS frame. For that, I'm going to send this FCS underscore valid. So these are my inputs and outputs of my TX underscore FCS. And next is CRC underscore rich is for storing the data, and CRC underscore next is for next data item, and data valid underscore D it's just for adding one cycle delay. Now I'm going to call this CRC underscore 32 parallel model, and I'm going to send the data in CRC underscore in and CRC underscore out. So CRC underscore out, I'm going to store it in my CRC underscore next. Now, after performing the CRC calculation, what I'm going to do is I'm going to basically generate a delayed version of data underscore valid over here. And this is the main logic which we are going to have. So when we are going to apply the reset, then my CRC register will be initialized to all Fs, and FCS underscore out is equal to 0, and FCS underscore valid is also equal to 0. Else, my FCS underscore valid is equal to 0. This is not needed over here. Let me comment it. Now, if init is made to 1, that is, I'm going to make reset of my CRC register to all particular Fs. But if my data valid is equal to 1, then whatever the CRC I have calculated using this particular CRC 32 parallel module, I'm going to latch that particular information into my CRC underscore reg. Now, if my data valid underscore D is equal to 1 and data valid is equal to 0, that means what I'm going to have is, so here my data valid will be equal to 1, and after one cycle data valid D will be equal to 1. It will have a one cycle delay. This is my data underscore valid, and this is my data underscore valid underscore D, delayed version of my data valid. Then what is going to happen is I'm going to basically do this particular operation of complementing my CRC register to my FCS underscore out. So this is what. So basically, I need to send the content of my CRC register to my output at the falling edge of data valid. That is what I need to do over here. And next, I'm going to make my FCS underscore valid is equal to 1. That's it. So this is how I'm going to perform a CRC operation. And what is the core logic of CRC calculation that we are going to discuss in our upcoming sessions. So yeah. So that's about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.